Most modern artificial intelligence models operate entirely on the foundational principles of statistical probability and sequential token prediction. Because of the massive commercial scale of large language models, the tech industry often defaults to a narrow definition of the field, equating all artificial intelligence with generative systems. These generative models have specific structural constraints. They are designed to predict the most likely next token in a sequence based on training data. This results in non-deterministic outputs and a heavy reliance on constant cloud-based compute power. Generative AI is one specific application of machine learning. Parallel to it is an entirely different class of system, cognitive AI. The architectural differences between the two are distinct. Generative systems are probabilistic, token predictive, and typically dependent on the cloud. Cognitive systems are deterministic, rule-bound, and sovereign, functioning independently of external model inference. A primary example of this cognitive architecture in practice is the Cognitive Mechanism System, or CMS. By mapping the internal architecture of CMS, we can observe how a system computes logic through mechanistic transitions rather than probabilistic generation. Treating language models as the sole definition of AI overlooks a foundational tier of computer science, the mechanistic solver. To understand the substrate of this system, we have to look past the user interface and focus entirely on the back-end logic. The CMS Core Reality Engine is a mechanistic solver, a component engineered to calculate state transitions through predefined rules. The engine's baseline input is the node-level triad. The engine processes this triad by fixed rules, producing a deterministic state unit. The state unit reaches a validation gate, checked for accuracy. Upon validation, the state unit re-enters the triad, updating the system. The cycle repeats until absolute stability. Through this process, logic resolution becomes a function of engineering and rule-bound stability. It calculates through direct transitions rather than scanning massive parameter sets, operating with very low compute requirements. It performs no token prediction, utilizing no probabilistic inference. This closed loop is the entirety of the CMS backend. This deterministic architecture demonstrates that a backend system can resolve complex state transitions without any reliance on a generative language model. If the reality engine handles the logic, what is the actual role of an LLM or generative model in this architecture? To maintain integrity, the system establishes a cognitive boundary, isolating the core engine. Large language models operate strictly outside, such as Layer 1, the terminal query analyzer. This layer translates natural language queries into the structured triads the engine requires. This translation is an assistive process for the user, not a cognitive one. On the output side, an optional expression layer takes the deterministic state unit from the engine and formats it into human-readable text. The architectural rule is absolute. The language model is prohibited from altering the computed state or influencing the engine's transitions. This design ensures the internal logic remains entirely insulated from the probabilistic noise inherent in generative systems. The external language model acts as a membrane, but it has no authority over the deterministic logic of the back-end engine. This division between cognition and expression leads to significant practical advantages in how the system is deployed. By removing generative models from the core backend, the system achieves computational sovereignty. This architecture allows for identical performance across different environments, whether it is hosted on a massive cloud network, inside a single localized hardware box, or in a completely air-gapped terminal. The core reality engine behaves identically across all three platforms because it does not depend on cloud-based inference to resolve its state. This provides the system with a level of security and isolation that is only possible through true computational sovereignty. This structural independence is what defines the system's intellectual property. The mechanistic substrate-level design is the foundation for its novelty and patentability. CMS shows that a system functions as an artificial intelligence product by computing cognition mechanistically rather than through generative guessing. By engineering AI through deterministic calculation, systems can achieve a standard of reliability and sovereignty that probabilistic models cannot reach.